Welcome and thank you for coming to the Organic Chemistry 2 test for review. So let's go ahead and start jumping into this. I do want to focus on those things which are particularly needful for you all, but if you want to interrupt me at any point, you can. We can pay more attention to certain things. But for now, I think we'll probably just jump into it, starting from the first one. Um, so in this first question, it's just asking you to draw what the product is. But I think when you're drawing the product, it's important to also remember the mechanism. So in this case, for example, if you have a Grignard reagent, methyl magnesium bromide, where is that likely to target? What position is that likely to target? And you can either use the hand symbol to point to it, or you can draw on the page. What do you think? Yeah, exactly. That triple bond. So basically, this CH3 methyl magnesium bromide acts as though it's a negatively charged alkyl group. So we're going to go ahead and take that negatively charged alkyl group, and it's going to come and attack here. Now that's of course going to break this triple bond and put an electron here. Now in this case, it doesn't say that I have excess, so it's not like we're going to get a continuous addition of these things. Plus, it would be a little bit challenging because of the fact that this does create a pretty strong base in the nitrogen, negatively charged nitrogen. But by following it up with water, so initially that's going to give you basically this. And then you have carbon double bonded to nitrogen. But then there's also another CH3 here. The nitrogen, however, is negatively charged. So this is very similar to an imine, or this is kind of like an imine. It's a deprotonated imine, so it's very basic, but it is kind of an imine. So when I add water to an imine, what does that tend to do? Well, it's actually going to convert the imine into a ketone, the double bond N into a double bond O. And it does this by a series of proton transfers, but essentially, and usually this is catalyzed by an acid, but it is possible to catalyze it with a base as well. I think, but in this case, essentially, this nitrogen is going to grab a hydrogen, and then water can go ahead and add to, or the nitrogen can then grab another hydrogen, basically. So let's say if this grabs, and I'll actually go ahead and, so if this nitrogen grabs two hydrogens, and then it grabs another hydrogen here, this thing becomes positively charged, making a great target for water. So what happens here then is the water can come and add here, and then you get basically a series of chemical reactions, or a series of proton transfers that ultimately results in the nitrogen being kicked off. And that full mechanism is, we're going to go through some similar mechanisms like that, but the full mechanism will ultimately lead to the transformation, which is going to give you, and then going to be a ketone, and then you're going to have that extra CH3 attached to the end. Any questions on that? All right, cool. Question number 2 says, what carbonyl compound and Grignard reagent would be needed to synthesize the following alcohol? carbonyl compound and a Grignard reagent. In this particular case, what you have, you could actually do a couple different things here. Basically, if you could either have the Grignard be this side, or Grignard coming out from this side, because it has to add to the carbonyl. So there's still the two possible places in which to cut it. So if you do the cut on the left, you end up with this MgBr, benzyl magnesium bromide, and you end up with this carbonyl compound. Now, if you cut it from the other side, and actually I should make this a little bit more consistent, so I'm actually going to show the cuts on this side with the black, representing the two black pieces over here. And then I'll do the cut with the blue, and I'll represent that with two blue pieces. So for that one, the carbonyl, you cut it at the blue point, the carbonyl would be this. And in both cases, they're aldehydes. And then you would also get a Grignard. The Grignard would be just that one carbon, CH3 methyl magnesium bromide. Looking at this, I think that you could make a case for either one of these working. You can make a case for either one of these working. I would say that there are two possible answers here. Which one might work a little bit better? Well, because Grignards are capable of elimination, causing elimination, although that wouldn't necessarily be as big of an issue here. It seems to me that perhaps the slightly better answer would be this one. But I really think that you can make a case for either one. Does that make sense? I don't know. I was thinking the benzoic position might be a more stable position to have the magnesium bromide on, with a negative charge could then potentially be localized into the ring. But I mean, it's not necessarily. One could also, I don't know. It's hard to say why one would be better than the other. I really think that both of them are probably about the same. I guess one could make a case that steric hindrance could play a role in potentially obstructing the carbonyl group in the blue one, but really the steric hindrance isn't that bad. Plus the nucleophile is pretty small as well. So yeah, I think it really could be either one. All right, let's take a look at this next one. So this is a carboxylic acid derivative problem. Kind of interesting. In this case, it wants you to draw the product of the following reaction sequence. Well, I want to kind of go through what each reaction sequence would end up giving you. So what would the thionyl chloride, the SOCl2, give you with this particular compound? What do you think? And you can feel free to talk. You don't have to if you don't want to, but you know. what would the thionyl chloride do? Add the Cl to which position? Where would it add the Cl? No, it wouldn't be. I mean, thionyl chloride, no, it wouldn't add it into the ring either. Thionyl chloride is it's an interesting compound. It is very acidic, but the key thing to remember about thionyl chloride is that it is the reagent to convert a carboxylic acid to an acid chloride. It's the reagent to convert a carboxylic acid to an acid chloride. So this is going to, the thionyl chloride is going to convert the carboxylic acid to the acid chloride. Then, if I have an acid chloride and I react it with an amine, that gives me another transformation. The carboxylic acid reacting with an amine will cause because the amine will be a good nucleophile, and it will come and attack this position here and kick out the chlorine, which is a good leaving group. And so that's going to actually give you an amide. You're going to end up with an amide. Whoops. Get rid of that. Let's try it again. So once you do step number 2 and add that amine, it's actually going to give you an amide. So you'll have a nitrogen here, NH, and you'll have 4 carbons attached to it. 1, 2, 3, 4. So that'll be the product of step 2. Now what's lithium aluminum hydride going to do? So this is a very important reagent. It's one that you should know how it works and know what it generally speaking does. Lithium aluminum hydride is going to be a reducing agent. It's going to reduce and get rid of this carbonyl. And specifically, the way lithium aluminum hydride works is it can reduce a carboxylic acid to an alcohol. But in this case, I don't have a carboxylic acid, I have an amide, and it will reduce an amide down to an amine. So what we actually have happening here, and step 4 is just to neutralize the basic and reprotonate it. To neutralize the deprotonated product. But effectively what you're going to get with combination of 3 and 4 is reductive amination. And so this is actually a reductive amination. When we form an amine by reducing, we form first the amide and then we reduce the amide with a lithium aluminum hydride. So you get, oh, actually that's gone because the lithium aluminum hydride takes that off. And then you get 2 carbons, an NH, and 1, 2, 3, 4. So this is your final product of the reductive amination. Does that make sense? Lithium aluminum hydride is effectively a nucleophilic source of hydrogen. So basically it acts kind of like an H minus. And the H minus from lithium aluminum hydride is going to attack the carbonyl and reduce it. So kick those electrons up, and then it'll follow up and attack again because lithium aluminum hydride is so incredibly basic, it can actually even kick off an oxygen. So you'll add 1 H minus and you'll add another H minus and kick off that oxygen on the O2 minus. But that's about as far as it can go because it's not basic enough to rip It's not basic enough to rip a hydrogen off a nitrogen. It's close, but it's not quite that basic. So it'll just like stop at that point. But anyway, lithium aluminum hydride is the reducing reagent when you want to reduce an amide into an amine, or when you want to reduce a carboxylic acid to an alcohol, because it provides that nucleophilic source of H minus. Does that make sense? All right, cool. Let's take a look at the next one. It says draw a stepwise mechanism for the following reaction. So one of the first things that I like to do when I'm actually doing a problem like this is I like to number the carbons. I'll start from the carboxylic acid side because that is actually the side that I would start with if I was numbering it to name it. So 1, 2, 3, 4, 5. Now see, this is a 6-membered ring. So this is 1. I can't go to the oxygen side. 1, 2, 3, 4, 5. So it looks like what happens here is that, you know, these are my 5 carbons. The only way this kind of attaches like this is if we ultimately are going to get some sort of a reaction where this oxygen comes, OH comes back around and attacks carbonyl. So basically, I have 2 groups here: a carboxylic acid and an alcohol. So the carboxylic acid and the alcohol will combine under acidic conditions in a process in a reaction known as Fischer esterification. Now, OH is not like alcohol. OH is not a super great nucleophile, so it may not necessarily go ahead and attack this right off the bat. But if you have an acid catalyst, you can activate that number 1 carbon as an electrophilic site, basically making it want electrons more. And what you do basically in the first step here is you're going to protonate that carbonyl. You're going to protonate that carbonyl to make it more attractive. So I have OH3 plus. It says H plus. I'm just going to put OH3 plus. I could put H plus, but basically, if there's water in there, it'll probably be in the form of H3O plus anyway. So I have the electrons here, and so what's going to happen is that these electrons are going to grab one of the hydrogens, and the hydrogen is going to leave its electrons on the oxygen, and you're going to get a protonated carbonyl. So here's our first product of protonated carbonyl. Protonated carboxylic acid carbonyl, for that matter. So I have a oxygen here, has a hydrogen here, and it has 1 lone pair of electrons. And 2, 3, 4, 5, and H. Okay. Now this oxygen over here also has a lone pair of electrons. So it can go ahead with a positive charge. Well, actually that's fine. Positive charge on the oxygen, which is going to make it more likely to pull those electrons towards itself, which makes that carbon and the carbonyl attractive to nucleophilic addition. So this comes here, kicks the electrons off to that oxygen. Okay. So then I go to the next step, and I have what's known as a tetrahedral intermediate. So I have this oxygen connected to a hydrogen with 2 lone pairs. I have this oxygen connected to a hydrogen with 2 lone pairs. And I have this oxygen, which actually, this actually came around. So I have the 2 lone pairs on this one, 2 lone pairs on this one. And then I have oxygen, so this is carbon number 2, 3, 4, 5, 6 is actually an oxygen. It says 1 lone pair and a hydrogen attached to it and a positive charge. This looks confusing, it kind of is. But one of the things that you can do here is just kind of like keep track. Okay, well, this is 1, 2, 3, 4, 5. I know I have to make the ring when that comes around and attacks. So I'm going to have to count 1, 2, 3, 4, 5, and there's my ring. Okay. Well, at this point, you gotta deprotonate that that H plus. So in deprotonating that H plus, I'm going to go ahead and grab this hydrogen, and these electrons are going to go to the oxygen there. That's going to give me this next compound. So this is now neutral. But, as you might imagine, having all these OHs around is not going to stay as it is, especially in an acidic environment. So, and these are actually equilibrium reactions. These are reactions that can go back and forward, back and forward. What drives the equilibrium forward is removing the water from the product. So if you remove the water from the product, if it has very little water, that's going to push it forward. But technically speaking, this is actually an equilibrium reaction. So I have my ring. At this point, the H plus acid is going to come back, and it's going to protonate one of these OH groups to get us an alkylonium ion, which basically is a fancy way of saying we now have water as a leaving group. Once again, this is equilibrium, and we have now our oxygen, 2 lone pairs, and we have our OH2 with a lone pair and a positive sign, and we have our OH on the left side, although it really wouldn't matter if you put it on the left or the right. And there we go. And at this point, since that OH2 is a good leaving group, this other alcohol can reform the double bond here and kick out the water as a leaving group. And actually, let me rewrite that reaction arrow because I'm not really totally happy with it. I'll show it going all the way to the bond. So that's going to give us a reformation of that carbonyl. Whoops, wrong color. the formation of the carbonyl. And here's our oxygen still. Here's our double bond, O. It now has a hydrogen, one lone pair of electrons, and a positive charge. At this point, the only thing that we need to do is have water come in and deprotonate that. And so water is going to come in and basically take that hydrogen off. And then those electrons are going to go back to the oxygen. And that's going to leave us with our final product. And you might ask yourself, well, hey, in the image above, the oxygen in the ring was on the other side. To which I reply, does it matter? Does it matter which side the oxygen is on in this case? No. Yeah, because it's basically, it's the same thing. If you just flip it around, it's the same exact thing. And just for the purposes of clarity, I'm going to go ahead and draw a separation line between the two parts of the mechanism so that we're not confused as to which part goes where. Any questions on that? Yeah, you'll find that a lot of these carbonyl, a lot of these alpha carbon chemistry questions, or even like carboxylic acid reaction mechanisms, involve a lot of proton transfers. So there's nucleophilic additions and proton transfers, and usually a lot of proton transfers. So don't get too lost on it. Just try to think, what's kind of take it one step at a time. What's going to happen next? And first, you got to activate the carbonyl by adding a hydrogen to it if it's in acidic conditions. If it's in basic conditions, the nucleophile will just add. After that, then you have to deprotonate the group that adds because it's now positively charged. Then you can protonate something else to make it a good leaving group. Then you can reform carbonyl, kick it out, and then deprotonate the other piece. So this is actually not one of the worst mechanisms. So I would expect her to have something about this. All right. Next it says, devise a synthesis of the following compound from benzene and any organic alcohols containing 4 carbons or less. So you have to start with benzene and alcohols of 4 carbons or less and use any inorganic reagents. So in this case, this is a little bit tricky. What I would recommend doing is, in a case like this, you have to look at the relative positions of your groups. So, is bromine an ortho-para director or a meta-director? Are your halogens ortho-para directors or are they meta-directors? Yeah, they're ortho-para directors. So, now, with some of these benzene reactions, para is usually the preferred location, but you will get both. However, it is sufficient to say that if you're going to do a bromination of benzene, or if you're going to well, I'll get to that in a second. But in this case, the first thing we're going to do is brominate the benzene. because we have our other group in the para position. Whereas if I look at that other group, is that an ortho-para director or a meta-director? Is that amide group an ortho-para director or a meta-director? I'm talking about this one right now. How can you tell if it's an ortho-para director or a meta-director? Generally speaking, you want to look to see if it is electron donating or electron withdrawing by resonance first and then by induction second. Does this nitrogen have a lone pair of electrons on it? Yeah, this nitrogen does have a lone pair of electrons on it, so it's electron donating by resonance. Now, is it also electron donating by induction? Well, no, but the truth is, in the vast majority of cases, the ability to donate electrons via resonance is always a more important factor than the inductive effects. The only case in which that's not quite true is the halogens, but even then it'll still prefer an ortho-para directing orientation for the things you add. So in truth, these are both ortho-para directors. These are both ortho-para directors. So if I want them para, would it be better to add one versus the other? What do you think? Which one would be better to add potentially? Why do you say that? Why would you say you want to add bromine first? I'm not saying you're wrong, I'm just asking. Yeah, but this is an NO2, right? Yeah, so yeah, exactly. But see, we could actually add bromine at any point. So there is a couple different ways that you could do this. It wouldn't be necessarily wrong to add bromine first, but if we're looking at the fact that both of these are ortho-para directors, which one is more sterically inhibiting? Which one's more sterically hindered? But which group is more sterically hindering? In other words, which group would block the ortho position better? The bromine or the amide group? The amide group. So I added the amide group first. It might minimize some of that bromine adding in the ortho position, don't you think? But I think it would work either way, because the other thing to consider here is if we it all depends upon the order. Let's say if we'll go kind of through both and then we can analyze them there. So if I had bromine, and typically if I FeBr, I think it's FeBr3 or AlBr3 you can use, and that's going to give us a bromination of that benzene. And we can just say put the bromine up here. Now, if we were going to try to add another group here, we could add the nitro group, and I believe that to do a nitration, call what those reagents are. I think it's like nitric acid and sulfuric acid. Oh, so I was thinking possibly NaNO2, but I think it would actually be nitric acid. NaNO2 would do something different. Nitric acid, HNO3, concentrated nitric acid into concentrated sulfuric acid. And the sulfuric acid is going to basically convert the nitric acid into nitronium ion, which would be a super electrophile I'll be able to add here. So that would give you this. The bromine adds first, then you get the nitro. And then from there, you can actually reduce that using, what is it, like zinc, mercury, Hg, a zinc amalgam, and HCl. Are those the reagents? I think those are the reagents. Yeah. You might not need the mercury. It might just be zinc and HCl. Is it zinc or zinc mercury? Can't remember. I think there's zinc mercury for something. I think this one you can get away with just zinc. Oh, with mercury? Okay. You might be able to get away with just zinc, but zinc mercury amalgam. And that's going to convert this into the, here's the bromine. Sorry, I kind of squinched that in there. And this is NH2. All right. The tricky part about this is the alcohols of 4 carbons or less. So the thing here is, if I need to get this from alcohols of 4 carbons or less, I have a carbon here and I have a carbon here. I need a 2-carbon group to add to this. I need all my carbons to come from those sources. So what I'm going to have to do is I'm going to have to start with an alcohol, a 2-carbon alcohol, basically. I'm going to have to start with CH3, CH2, OH. Now, to be able to react with an amine, in order to get it to produce an amide, I'm going to first need to convert this. I'm going to have to oxidize this into a carboxylic acid or carboxylic acid derivative. And to get this into a carboxylic acid, I'm going to use Jones reagent, which is basically chromic acid, or more precisely, we're going to form the chromic acid in situ, which is in the reaction vessel, with Cr2O7 and sulfuric acid. And that'll break down to form chromic acid. And that will give us a CH3, C double bond O, single bond OH, which I can then convert to an acid chloride with thionyl chloride. Because even though technically speaking there are ways to get a carboxylic acid to combine with an amine to form an amide, the reaction is just a little bit less problematic with an acid chloride. So I'm going to convert the carboxylic acid to thionyl to acid chloride using thionyl chloride SOCl2, and that's going to give me CH3C double bond O Cl, which when I combine it with this guy, I'll actually go ahead and circle this. Combine these two together in the same solution, it's going to give you this. So there's your synthesis. Alternatively, you could react the thionyl chloride you could actually, well, you could nitrate this benzene ring first and then reduce it with the HCl and zinc amalgam and then follow it up with a reaction with the with the acid chloride. And if you do that, then you can follow up at the very end, and the last step would be the bromination. So basically, it's the same exact steps, except you just leave the bromination to the end instead of doing it at the beginning. I think you could really do it either way. And if I'm honest, I mean, nitrate is actually somewhat, this is actually NO2, sorry, my bad, NO2. Nitrate is actually kind of a sterically hindered group when adding, so that might actually inhibit the addition at the ortho position next to the bromine. So I'm not necessarily sure which one would give you the better yield, but both of them I think would actually be viable. Any questions on that? All right, now let me know if you want to skip ahead to a particular question, because admittedly, we're already about an hour into this, and I don't think we're going to get through the whole thing. So if there's questions you specifically want to go through, we can definitely do that. Question number 6, though, is really easy, though. Do you need me to go through question number 6? I can do it real quick if you want. It doesn't take long. Question number 6 basically just wants the most stable enol tautomer. Well, enol tautomer, it says, yeah, right for the reaction to form the most stable enol tautomer for the following compound using hydroxide as a base. And I wonder if she means enolate. And I wonder if she means mechanism. Because if she means just write the most stable enolate, then that would just be this. The most stable enolate would just be this. You'd basically just have the OH minus and she doesn't say mechanism, which makes me confused. I don't know exactly what she means when she says draw the most stable enol tautomer. But then I could basically have this go up here, and these that would cause these electrons to go up here. So that would give you this enolate. It'd be basically H3C, C single bond, oxygen, 3 lone pairs of electrons and a negative charge. And then I'd have a double bond here, a CH, and then I have a single bond here, carbonyl. Now, if she actually did want the actual enol tautomer and not the enolate, and she wanted you to write the mechanism, the base catalyzed mechanism for creating the enolate, then what she may be actually referring to is something like this. She may be like, oh, okay, well, what about you could then take water potentially, and water could follow up here, and you could get the negatively charged oxygen coming over here and grabbing the hydrogen from the water and reforming the base. So this is base catalyzed tautomerization. And of course, this is reversible. And this is reversible. And then that would end up giving you this enol tautomer, which would be the C single bond OH, a double bond down here to not carbon, not oxygen. I don't know what it's going. Carbon, the hydrogen here, and a double bond oxygen here, and then a CH3 here. This would be the most stable enol tautomer because there's conjugation throughout the ring. or not throughout a ring per se, but there's conjugation throughout. The oxygen in the OH is actually sp2 hybridized because it's capable of donating its electrons in resonance. The carbon is sp2 hybridized here, so basically this is sp2 hybridized, this is sp2 hybridized, this is sp2 hybridized, this is sp2 hybridized, and this is sp2 hybridized. So you have sp2 hybridization across 5 atoms, gives you a fair amount of resonance localization. So that would be the most stable enol tautomer. Does that make sense? So let's go to the next one. Now draw the organic product from the following reaction. So basically it's the same compound that we just looked at. It's LDA, and then followed by a 4-carbon butyl bromide, basically. So what would the LDA do? Yeah, it deprotonate the middle alpha carbon. And this would basically be quantitative because LDA is such a ridiculously strong base. Even though, yeah, maybe this technically could be considered an equilibrium, but the equilibrium has shifted so far over to the product side, it's not even worth thinking about the reverse reaction. So this will get quantitatively deprotonated. So you're going to end up with only 1 hydrogen there and a lone pair of electrons and a negative charge. So it'll be a lone pair of electrons and a negative charge on that carbon. So that carbon, and you probably have an idea what that negative charge is going to do, right? What's it going to do? Substitution, right? Yeah, attack the alkyl halide. Oh, the SN2 substitution at that point. And so after that does the SN2 substitution, you basically end up with this, CH3, double bond O, carbon, CH, CH2, 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 and CH3. And some of you, I know who you are, who like to try to overcomplicate things, may try to do some elimination or whatever, but in this case, no. All you have to do is leave it like this, because it's not, after the LDA was used initially to make it into a base, but you don't actually have anything else to do at this point. The butyl bromide has added, there's no acid or base to continue any sort of elimination type stuff. So no, this is all that happens pretty much. And you just get that nice convenient little alkyl group added between those two. Okay. So the next one is kind of fun. I always like synthesis problems. Synthesize the following compounds starting with 3-pentanone. And you may use any other organic or inorganic reagent. You see, the interesting thing here is that the backbone, 3-pentanone, is still intact in the overall product. So this isn't an enol. Well, it is an enol, but it's not like it's not like one of those enols where the alkene is directly connected to the alcohol. You actually have this space out. And so that's going to be a little bit tricky to get that double bond over there. You're going to need to have something to eliminate, right? Well, what could that have come from, potentially? What could this have come from? If I use the principle of backward design or retrosynthesis, shall we say? But sometimes I like to work backwards and sometimes I like to work forwards. But for this, one of the things I know from the alpha carbon chemistry chapter is that I can actually get a halogen on this spot right here. And if I can get a halogen on that spot, then that means that I could potentially get a double bond there as well, or like between those end carbons like that. So what I might actually do here is maybe I'll start with the forward design this time. So if I were to use Br2 and H3O plus, Br2 with a little bit of an acid, I can potentially get I could get this converted into its enol form, and that would allow me to form the alpha bromo ketone. And so that is going to transform this ketone from this to this. Now, what would I use to cause the elimination? What are some things you can use to cause elimination with the bromine? Now, that's a secondary bromide, right? That's a secondary bromide, right? Going back to Gen Chem 1. Well, in E2 elimination, you need to use a strong base. That secondary bromide can actually be eliminated by pretty much any base. But yes, in this case, if we want to ensure that it doesn't try to act as a nucleophile with the ketone, and we want to ensure that we get the less highly substituted side, then it would make sense to use terbutoxide, that big, fatty, bulky base. And of course, that would be terbutoxide in terbutanol as a solvent. But that's going to give you the elimination that we need to form this. Okay. So now what do? I look pretty close to my final product. What could I do here to give a nice mild reduction of that ketone without affecting the double bond? What would be a good reducing agent to reduce the ketone without affecting the double bond? You need to know these reagents. I'm looking for a reducing agent. Get that ketone down to an alcohol. In this case, it looks like you could use lithium aluminum hydride. So you could use lithium aluminum hydride, but you could also, yes, definitely use. I first thought of sodium borohydride. An electron-rich double bond, like a carbon-carbon double bond, is not going to be attractive to a negatively charged electron. So yeah, lithium aluminum hydride is more aggressive, but in this case, you could still use it. So you're absolutely right. You could use lithium aluminum hydride, but sodium borohydride would also work as well. So either one of those you could use to reduce this to an alcohol. Yeah, either one of these you could use to reduce to an alcohol. And then predict the product for the following reaction. Very well, very good on that number 9, or number 8. So predict the product for the following reaction. In this case, lithium diisopropylamide, that's a strong base, right? One could try to make the case that it could maybe be a nucleophile, but in this case, it's typically just going to tend to go after the most acidic hydrogen, and the most acidic hydrogen is going to be either this one or this one. Now, in this case, there's a secondary consideration because if this rips off one of those hydrogens to connect as a nucleophile, what would that nucleophile do? If I deprotonated one of those positions, what could that potentially do? Attack itself, yeah. Intramolecular, it's be an intramolecular reaction, intramolecular SN2 substitution, kicking out the bromine. So with that, you want to probably try to form the most stable ring possible. And if I'm looking at this, if I removed the hydrogen on the right, that would get me a ring that is 1, 2, 3, 4 carbons. 4 carbons. It would be a cyclobutane. Well, there's significant angle strain with cyclobutane, steric strain and angle strain. So what about if I did this one? 2, 3, 4, 5, 6. A 6-membered ring is just about perfect. You minimize angle strain and you minimize steric repulsions with a 6-membered ring. So in this case, it will be one of these guys that gets likely to be taken away. And then the electrons are going to come and attack. Oh, electrons are going to come and attack. I don't know what happened there. Let me try that again. The electrons are going to come around and attack that position. Now, this is tricky because what I would recommend that you do here is I would recommend that when you draw your ring, make sure that you number the carbons before you add any groups. So I know I'm going to have a 6-membered ring. Just because, you know, maybe you like to have the carbonyl on top, that's fine, you can. But you have to remember, okay, well, if that's the carbonyl at top, that's number 2, that's carbon number 2. Now, carbon number 1 can be on either end of this, but I'll just go ahead and put carbon number 1 here, which makes this one carbon number 3, 4, 5, and 6. So what's attached to this ring? What else do I have to draw besides this? There's a group attached to which carbon? Yeah, there's a group attached to carbon 3. So I have to draw my C, what is that, C6? Or is that C8? Can't even read that. I gotta zoom in. C6H5, so that's a phenyl group. This is a C6H5 or phenyl group that's attached to this. And there you go. That's how you would do that problem. There's your product. Makes sense? Don't underestimate the power of numbering. It really can help. Yeah, I can jump to 14. All right. Alval condensation, Claisen condensation. Looks like this one is going to be a, oh, that's an interesting one. Mixed algal condensation, that is. Devise a synthesis of the following compound from aniline. I don't want to do that. Oh my goodness. You do throw the hard ones at me. Jessica, why can't you ever just ask easy questions? No, aniline's going to start with this, NH2. The interesting thing about this is there's no nitrogen in the actual product, so we need to find a way to get rid of that nitrogen. And one of the ways in which we do this is by the utilization of what's referred to as the diazonium ion, I think it's called. It's basically an N triple bond N, okay? And we make a diazonium chloride salt. So here's the deal. I can actually get, and this is why I was thinking of the NO2 from the other thing. So that's not how you get the nitrate, but that is how you get the diazonium ion. I can actually start by using the NaNO2 and HCl. The NaNO2 and HCl in combination are effectively going to end up giving me this diazonium ion. And I'll be honest, I don't remember the mechanism offhand. I'd probably have to reference the book, and I'm not even sure if it's in the book, but it probably is, but I'm not sure. This is going to give you the diazonium chloride salt. So this is a positively charged diazonium and a negatively charged chlorine. All right. The diazonium salt is actually a pretty decent leaving group, if I recall correctly. So it actually makes this a really good leaving group for just plain old nucleophilic substitution, which usually doesn't happen in a benzene ring. In this case, this can work with copper cyanide. So copper cyanide, CuCN. And that will effectively act as a nucleophile. I don't think sodium cyanide would work, NaCN. There's a function that the copper performs, and I'm not remembering it perfectly at the moment, but that is important, though, in this particular reaction. So you end up with a cyano group adding to the benzylic ring and the diazonium group being kicked out. Okay, so then what happens next? Well, somehow I have to get that bromine in a meta position, so I need to make this a meta director. Well, technically speaking, this is actually electron withdrawing by resonance, and it also, I think, is electron withdrawing by induction. So at this point, if I wanted to, I really could go ahead and add the bromine if I wanted to, but I could also go ahead and wait till later. So I think I'm just going to wait till later. You could do it first, or you could convert this into a carboxylic acid first. And I think I'm actually just going to convert it to carboxylic acid first. I'll use H plus and H2O, maybe add a little heat, and that's going to go ahead and convert this to a carboxylic acid group. That's one of the ways in which we make carboxylic acids. We can use a cyano group, and then we can turn it into a carboxylic acid. Now that I have this electron withdrawing group, I can go ahead and, this is definitely a strong meta director. I can follow this up with a little Br2 with either aluminum bromide or iron bromide, FeBr3. And that will be a meta director. Not the bromine, but rather the carboxylic acid group, because it's electron withdrawing by resonance and it's electron withdrawing by induction. So you get the best of both worlds here. Resonance and induction, both are electron withdrawing by carboxylic acid. So this is going to give me my bromine here. Well, now I have to find some way to get this back to just a methyl group. I want to get rid of it completely. And in truth, there's actually a couple different ways to do this. But I don't know, the way that kind of like pops into my mind right away is to do reduction. So I can use lithium aluminum hydride, H4, followed by water. You might be like, well, that doesn't help. It's an alcohol. And I'm like, yeah, it is an alcohol, but we're not done yet. And then I can take my alcohol here and I can oxidize it with a little PCC. Oxidizing it with PCC is going to give you a aldehyde. Yay. And you're like, why would I want an aldehyde? What good does that do? Well, the aldehyde allows you to use either Wolff-Kishner reduction or, in this case, the other reduction you can use is the zinc amalgam with HCl. That will also get rid of this. And I don't know if I like the Wolff-Kishner reduction, partially because I can never remember the reagents, but I think you could use the Wolff-Kishner reduction here. I think it's like an azide, or not azide, it's a NH2, NH2, can't remember what it's called. But yeah. Oh, why am I said HCN? I mean HCl, my bad. That Wolff-Kishner in the brain. And that will completely, this is called a Clemmensen reduction. And a Clemmensen reduction will actually reduce this into a single bond, not a double bond, forget what I do. Single bond CH3. And then I also have the bromine here. Are there simpler ways to do this conversion? Maybe. Let me know if you find it. There may be simpler ways to do this conversion. But I'm not totally sure what they would be offhand. Yeah, no problem. What's that facial expression? Oh my goodness. Make me laugh. Okay. Yeah, like I said, there may be a simpler way to do this, but I'm not totally sure what it would be. Because I don't think that the Clemmensen reduction works on carboxylic acids. So I don't think you could just go straight to the Clemmensen reduction from the carboxylic acid. I mean, maybe you can, but I don't think you can. I think it requires a ketone or an aldehyde. If you could do a Clemmensen reduction with a carboxylic acid, then you'd be good. Clemmensen reduction with carboxylic acid. I want to see if that's a possibility. I don't think it is, but yeah, carboxylic acid does not undergo Clemmensen reduction. So yeah, that's going to work. I think I have to do this. Okay, cool. All right, any other questions? I guess we're almost out of time here. Although if you wanted to go over one more question, I could be convinced. By the way, I don't know if you noticed, but number 13 was a leading question for number 14. But it says, what is draw the product of the following reaction? For number 13, the product of the following reaction, this is easy. This is just that diazonium salt. N triple bond N positive with a Cl minus here. So if you got the answer right for 13, then when you went to 14, you would already have the first step of knowing what to do. So she kind of was nice to you in this case by putting this here, like, or nice to her students that year that this test was given, and put 13 right before 14 to kind of like be like, yeah, you look at this one. Okay, hint, hint, what do I do now? 14 is kind of an extension of that. Well, I'll tell you what, go ahead and take a stab at some of these other practice problems. Yeah, you're welcome. Now take a stab at some of these other practice problems. The only ones I think we didn't get to are like, we did through 9, but I think we didn't do 10, 11, and 12. We did everything else. We did all of them except for 10, 11, and 12. So go ahead, feel free to give those 3 a shot. Those are all alpha carbon chemistry. You have to do with aldol condensations and Claisen condensations. And then if you have any questions, feel free to stop by the Science Learning Center. We're open till 8 tonight or 10 to 4 tomorrow. Yeah. Thank you for coming. It's been fun.